All right, good afternoon, everyone. We have come to the second lecture. Today we talk about so-called hydration. Okay, so hydration is the chemical reaction between the cement particles, also we call that compound, with water. Okay. From last time we learned there's different type of oxides. Also we call that constituent materials in molten Portland cement. So we have Lisa, right? Line, I is for ferric oxide, S is for silica, and A is for alumina. Okay, so these are four major. Also, we have the shorthand for these oxides, some minor chemicals like magnesium, carbon dioxide, and water. Okay. Also, we learned we have major compounds in cement. We have C3S, C2S, C3A, C4AF, and the gypsum. Okay. So today we're going to look at how these different compounds will react with water and what are the end product, or we call that hydration products. Here shows what is the particle size distribution for cement. As we can see, the medium size is around 10 to 20 micrometer. Okay, so that is the typical size for Portland cement. There are five major types of cement. Okay, as we can see from this video, what they are and where they are used in different type of applications.
There are 5 types of Portland cement produced in mills like you see here. These different types of Portland cement can be used to suit various design and construction needs. Almost all uses of concrete can be made with type 1, a general all-purpose cement suitable for buildings, bridges, floors, pavements, and precast structures. But some concrete structures require special needs. These precast pipes are exposed to sulfates in the ground. A type 2 cement gives the concrete moderate resistance to sulfate attack. The concrete for this winter placement will set and harden slower. A type 3 cement can be used to give higher strength concrete at an earlier age than type 1. Its application is similar to using a type 1 with a chemical accelerating admixture. The concrete for this dam will generate a tremendous amount of heat during hydration using a type 1 cement. A type 4 cement minimizes the heat for these massive structures. This sewage treatment plant is exposed to high concentrations of sulfates. A type 5 cement gives the concrete protection against these sulfates.
All right. There are 5 major types of cement. Okay, which is defined by ASTM. Sorry. Okay, so ASTM C150 is called Standard Specification for Portland cement. Okay, under that we have 5 different types. Okay, so type 1 is called ordinary Portland cement or general purpose. Okay, so that's the most used cement. Type 2 is called moderate sulfate resistant cement. Okay, so in the environment, mostly coming from the groundwater or soil, sulfate may cause concrete to crack. We call that sulfate attack. If there's a potential sulfate attack for concrete, we may consider use type 2 or type 5 cement. Okay. Type 3 cement is called high early strength cement. Okay. This type of cement will harden faster. Okay, for certain type of application, we use that. And type 4 cement is low heat of hydration. So that will reduce the temperature generated at early stage, because hydration is a chemical reaction that will generate a lot of heat. In mass construction such as dam, reduced temperature will reduce the potential for cracking due to high temperature. Okay. And type 5 cement is called sulfate resistant cement. Okay, similar to type 2, but more resistance to potential soffit attack. There's some other type of cement depending on whether we have air entraining agent or some other chemicals in that cement. Then we call that type 1A or type 1 cement with air entraining agent and so on. Okay, but these are the 5 major types.
Professor?
Yes.
I have a quick question.
Sure.
When you say sulfate attack, what do you mean?
That is the sulfate coming from the groundwater or the soil. So that will react with one of the hydration product in concrete, which is we call the monosulfide aluminate. You're gonna see the chemical reaction in a moment. So that will cause another new product we call the ethylene guide. So ethylene guide will expand and cause concrete to crack. Okay, when concrete crack, all kinds of problem will generate. So we do not want that.
Right.
So yeah, okay. So we will talk more about that. Okay, good questions.
Thank you.
Yeah. So C150 lists a common chemical and physical requirements for a different type of cement. So it must be a hydraulic cement, including mostly hydrated calcium silicate, which means C3S and C2S, as we discussed a moments ago. Okay, and also some limitation, for example, less than 6% of magnesium oxide, because too much of that will cause concrete to crack. We call that unsoundness. So magnesium oxide will generate magnesium hydroxide, which will cause concrete to crack. Okay, so really limit amount of that. And some other requirement, such as less than 0.75% of insoluble residue, or if low alkali cement is designed, then we should limit amount of percentage of sodium oxide plus 0.658 times the percentage of potassium oxide. Okay, too much alkali may cause concrete to crack due to another durability issues called alkali silicate reaction, or ASR, which again we'll talk much more in future lectures. Okay. There are some more physical requirements for the fineness, setting time, okay, and the strength. Okay, we can see that. Here is some of limitation for the compound in different type of cement, as we can see from here. We will talk why we should limit, for example, the percentage of C3A less than 8% for type 2 cement, okay? Or why limit amount of C3S and C3A, we can reduce the heat, reduce the temperature rise in concrete. Okay, these are the general requirements from C150. Here are some of the key points to help us remember these details. Okay, first of all, the rate of hydration, or how fast this compound reacts with water, is ranked as this: C3A more than C3S, more than C4AF, more than C2S. Okay, and heat of hydration, which is depending on for each gram of this compound, how much heat enjoy is produced, are quite different, and you can see from the table in the textbook. And the hydration product of C3A, which we'll see in a moment, may react with the sulfate from the environment, cause concrete to crack. Okay. So here are some more physical requirements, such as the strength. For type 3 cement, the 1D strength should be at least 12 megapascal, and so on. You can just read it from there. Okay. And for the initial setting time and the final set time, setting time is when concrete achieve a certain strength. Okay, initial set time should be at least 60 minutes. Final time no more than 10 hours. Fineness is a measurement of the surface area. So 280 square meter surface area for every 1 kilogram of cement. Okay, so that's the requirement for fineness or surface area. And also requirement for the maximum amount of sulfate oxide. Okay, so depending on the requirement for sulfate attack. Here is an example showing us chemical analysis, most likely XRF, showing the oxides for certain cement samples. Okay, together with the specs limit. For example, silica oxide percentage, the limit is at least 20%. The result is 21%, so pass. And so on for other type of oxide. Okay, and this is compound calculated based on the bulk calculation, as we discussed at end of last lecture. Okay, and also the requirement for the surface area. Okay, the strength at 1 day, 3 days, 28 days, and so on, and also the setting time. Some other requirement for the compound percentage. Right, so 5 different type of cement we should use depending on the application we use. Type 1 cement is called general purpose, can be used in Portland cement road, pavement, slab on grade, bridges, buildings, and so on. Type 2 cement and Type 5 cement is called moderate sulfate resistant cement for Type 2, and Type 5 is sulfate resistant cement. Okay, sulfate is coming from the environment, most likely from the soil or groundwater. So when the concrete, such as this pipe, underground pipe, if the soil has a lot of sulfate, we may consider to use Type 2 or Type 5 cement. Type 3 cement is high early strength cement. In that cement, the chemical reaction is faster than Type 1. As a result, the temperature in the concrete at early age is higher. And also the concrete will set faster. So under winter construction, we do not want the concrete to freeze, when the temperature is very cold. Okay, so use Type 3 cement may compensate the cold weather. Or for the emergency repair of the pavement, we want to open the road faster, so we use Type 3 cement, so the concrete will get its strength faster, so we can open the road sooner. And here shows the precast plant. The members of precast members is assembled together, and this precast members is prepared in precast plant. Okay, we can use Type 3 cement in precast plant because we can increase the production rate. The concrete will set faster. We can make more members in the same time. Okay, so here are some of examples we can use Type 3 cement. Type 4 cement is low heat cement. In mass construction, such as this huge pier, reinforced concrete pier, or concrete dam, we pour a lot of concrete in one place. Okay, the inside of concrete, the temperature may be very high, because first of all, hydration will generate a lot of heat, and also concrete is very good thermal insulator. So inside the concrete, the temperature may be very high. If the temperature is too high, it will cause a lot of problems, including flash set, the strength may also be reduced, and also big temperature difference between inside and outside of the concrete may cause the concrete to crack. Okay, so if we use type 4 cement, we can reduce the temperature gradient and reduce the potential for flash set. Okay, we're gonna talk about that more in future lectures. Okay. Then let's look at cement hydration, which is the chemical reaction between water and cement. Okay, when we mix water with cement, chemical reaction called hydration will occurs. Okay, so the cement grain will dissolve, diffuse, and precipitate. So here I shows three words. Okay, so diffuse means dissolve. Firstly means the water will dissolve the cement grain. Okay, and then hydration product will precipitate on the surface of remaining cement grain. Okay, and then we will have more hydration product. Water will diffuse into the cement grain, which is right now covered by the hydration product, and release more cement into the water. So we call that diffusion process. Okay. The chemical reaction is exothermic, which means heat will be released. Okay. And heat signature is very important to characterize the material development, depending on the type of compound in the cement. All right, here is an important slide showing us chemical reaction for different compounds. Remember, we have C3S, C2S, C3A, and C4F. Okay, so let's look at C3S. C3S will react with H. H here is water. It will generate calcium silicate hydrate. Okay, they have different names. Plus CH. Remember, C is a shorthand for calcium oxide, and H is water. Okay, so CH means calcium hydroxide, CaOH2. C2S also react with water, generally the same thing, CSH plus calcium hydroxide. Okay, but the difference between these two is C3S react faster compared to C2S. Okay. The strength of concrete is mainly provided by calcium silicate hydrate, or CSH. CSH is the strongest hydration product from all these chemical reactions. Okay, keep that in mind. The reaction of C3A with water is pretty complicated. And remember, we need some gypsum to slow down the hydration. Okay, so even with gypsum involved, the reaction is very fast. Okay, C3A plus gypsum plus water, it will generate a so-called ethylene or AFT. Depending on the ratio of C3A and gypsum, C3A may also generate ethylene to generate monosulfide aluminate, another potential hydration product. Okay, so the name for monosulfide aluminate is also called AFM. So that means for every one part of C3A, there's a one part of aluminate. Okay, M is for mono. AFT means for one part of C3A is for aluminum. We have 3 parts of sulfate. Okay, T is for tri or 3. Okay, remember the name of hydration product for C3A. Now we talk about type 2 and type 5 cement. They are called sulfate resistant cement. But what is sulfate attack? So if there's a sulfate from the environment, such as the soil or groundwater, so the sulfate in the form of gypsum will react with AFM, which is monosulfide aluminate, one of the potential products of C2A, it will generate ethylene guy again. AFT is ethylene guy. Okay, so this chemical reaction will cause expansion of concrete. After concrete hardens, it is very weak. So when we have expansion inside the concrete, that will cause concrete to crack, and we call that sulfate attack. So ideally, we will generate all the C3A, transfer all the C3A into ethylene guy before concrete hardens. Okay, so if there's any monosulfide aluminate after concrete harden, and then we have some sulfate from the environment, then that means potential troubles, because AFM will react with sulfate to generate ethylene guy again after concrete hardens. Okay, it's kind of complicated, but we're gonna talk about this in much more details later. Okay, so this is reaction for C3A. For C4AF, is pretty similar to C3A. Okay, here show the equation for C4AF. So the ferrite plays similar role as aluminum. Actually, these two oxides can interchange each other. And the reaction of C4AF is slower compared to C3A. And there's no expansion caused by late ethylene guy formation. So that means C4AF will not cause potential problems due to sulfate attack. So better sulfate resistance. Right. Let's look at the hydration product. The first one, or the most important one, is CSH. Okay, so this is silicated barium hydrate. We have different names called CSH or C-S.H or CSH gel. Sometimes we also call that tobermorite gel. So tobermorite is the natural minerals, has similar structure as CSH. Okay. This is a different name for ethylene guy. Okay, we can call that AFT. Okay, short for aluminate ferrite trisulfate, which means for one part of aluminate, we have 3 parts of sulfate. Okay, AFM, it can also be written like this. C4A-S is sulfur H12, also called monosulfate or monosulfide aluminate or AFM. Okay, the full name is aluminate ferrite monosulfate. Okay, so CSH, ethylene guy, monosulfide aluminate. So these are 3 major hydration products, and plus calcium hydroxide. Okay. So C3S does produce more calcium hydroxide than the same molar fraction of C2S. So based on the equation showed a couple of slides earlier. Okay. And the CSH produced by C3S is the same as the CSH produced by C2S. Okay. And the exact composition of CSH is actually not fixed. Okay. It's not C3S2H3. It is changed depending on many factors. And also we have chemically bound water to CSH gel. All right. Some more facts about ethylene guy. Okay, the equation may not be exactly like this. Okay, and some of ethylene guy is sulfate deficient. Okay, and some of the silica can replace alumina, and sometimes even ferrite can replace alumina. And monosulfate, okay, is usually produced by secondary reaction of ethylene guide with C3A. However, it may be produced directly from C3A with water and sulfate, depending on the ratio of C3 and gypsum. Okay. And here shows the strength development of the major compound, C3S, C2S. So both these two generate CSH and CH, but CSH, C3S react much faster compared to C2S. Okay. For C3A, the rate of hydration is even faster than C3S, but let's look at the strength. The strength for C3A hydration product is much lower because if you generate AFM or ethylene guide, the strength of these two is much weaker compared to CSH from C3S and C2S. Okay, so the strength of concrete is mainly coming from C3S and C2S, not from C3A. Okay. So the final strength is determined by C3S and C2S, and if we want higher early strength, we should increase the percentage of C3S because it reacts faster. And again, remember CSH is the hydration product providing strength of concrete, not ethylene guide, not monosulfide aluminate. Okay. For different type of cement, depending on application, we can change the percentage of different compound because they will react differently. Okay, for example, for type 3 cement, which is high early strength cement, we're gonna increase the percentage of C3S. Why? Because C3S react faster compared to C2S. Okay, for low heat options, we should reduce the percentage of C3S, increase the percentage of C2S for the same reason, because C2S will generate less amount of hydration heat. All right, and here shows different type of cement, the strength development. For high early strength cement, type 3 cement, the early strength will be higher. However, type 4 and type 1 cement, the strength will catch up and exceed type 3 cement at later age, after 3 or 4 months. Okay. And ESTM C150 shows us some of the limitation for different type of cement, for different compound. Okay, for example, for type 2 cement, we should limit the amount of C3A to a certain percentage. Why? Because remember, sulfate attack is caused by formation of ethylene guide after concrete hardens. Okay, where ethylene guide coming from? It's coming from C3A. So we limit the percentage of C3A in sulfate resistant cement, type 2 and type 5 cement. Okay, for type 3 cement, for example, we need to increase BF is called blade fineness, which is a measurement of the surface area. Okay, so increase the surface area of type 3 cement, the hydration speed will be faster because we have more contact area between cement particles and water, so we have faster hydration. Okay, if we want higher hydration speed. Okay. For type 4 cement, the low heat cement, we want to increase the percentage of C2S because the reaction speed of C2S is slower. Okay, so we better understand this. by studying the chemical reaction for different compound. Alright, so then let's look at the chemical reaction in more details. Okay, we know we have setting time. We have initial set time and final setting time. That's the two time between true liquid and the true solid, true rigidity of the concrete. Okay, and then concrete will continue to gain strength after several weeks. All right. So initial set time is defined as time when concrete can no longer be handled and placed. Okay, it has some strength, become hardened. And final set time is the time at which hardening actually begins. Okay, so after the final setting time, we can detach the formwork, we can even work on the concrete, so it is strong enough. Here shows the measurement for initial and final setting time for mortar samples. Okay, so we use a needle with a certain weight and certain diameter. Okay, the sample of mortar is mixed here, and for every 5 minutes or so, we try to penetrate the sample with a needle, and we record how much settlement, which is the penetration depth. Okay, so we connect all the data points as a curve, and initial set time is when the penetration begins. Okay, less than 25 millimeter or 1 inch. And final set time is when the needle can no longer penetrate the mortar at all. So 0 penetration depth. And the water cement ratio of the paste or mortar is 0.4. Okay. So W over C is the ratio of water to cement. This is the most important factor controlling the strength of concrete. Okay. Right, so let's look at the hydration in more details. So here shows the heat of hydration over time. Okay, so the XL is the time, the YXL is rate of heat evolution. Okay, so depending on the slope, the shape of the curve, we have 5 different stages. Okay, so the first stage is called rapid heat evolution, which is less than 15 minutes. Okay, we also call that hydrolysis. So that is when water faster dissolve cement, and cement will generate a lot of ions into the solution, into the water. Okay, ions including calcium and also hydroxide is released from cement grain into water. Okay, then we have stage 2 or dormant period. Okay, as we can see from here, there's not much going on here. Okay, the heat of revolution is very slow. Okay, stage 2 will range from 2 to 4 hours. So that's the time for the transportation of concrete. Okay, the reason we have stage 2, the reason why we do not have anything going on here is because the hydration product will not be generated in this stage because the concentration of ions such as calcium and hydroxide ions is not high enough. Okay, so concentration of these ions is increased during the stage 2 until a certain level. So we call that threshold concentrations. Okay, the threshold concentration is achieved here. Okay, at end of stage 2 or the beginning of stage 3. Okay, so after the so-called threshold concentration achieved, then hydration product will begin to produce. We're going to have initial set time. We have more and more hydration product produced. And at the end of stage 3, which is also called accelerating stage, is the final set time. Stage 3 is about 4 to 8 hours. Okay. After that, the concrete is strong enough, we can detach the formwork, but the hydration is still go on. Okay. So stage 2 is called deceleration stage. Of course, the concrete is no longer workable. Actually, at stage 3, we cannot finish and mix the concrete anymore. Okay. Then stage 5 is called steady state. Okay, we have a so-called diffusion controlled process. Okay, so this movie shows us what's going on into the hydration stage. Okay.
This is a sketch of cement grains suspended in water. The solid hydration products form coatings around the particles of cement and gradually fill the space between. When the coatings first begin to impinge, setting occurs. There is a steady development of strength as the coatings grow together. The amount of strength attained by the mixture of cement and water depends on how effectively the space between the grains is filled up. Concrete will harden within a few hours, but hydration continues for weeks, even years after placement.
Alright, so when you mix water with cement particles, you can think as the cement particles suspended in the water. Okay, and the cement particles are not connecting each other. Okay, because we have a lot of water in it. Okay. When we have hydration product, okay, this hydration product will precipitate on the surface of the cement grains. So we have more and more solid. Okay. So at a certain stage, the nearby particles will connect and stick together. So we have hardened concrete. We have initial and final set time. As we can see from here, this is the early hydration product formed in the water. This is cement particles suspended in saturated lime and calcium sulfate. Okay. So we can see clearly the hydration product, which looks like a sheaf of wheat, precipitate on the cement grain. Alright, so here's another picture, early hydration products. Okay, so precipitate on the surface of cement grain. Okay, so remember the three verbs again: dissolve, diffuse, and precipitate. Okay, so first of all, water will dissolve ions such as calcium and hydroxide from the cement grain. Okay, when the concentration of these ions achieve a certain so-called threshold concentration, then the second verb, precipitation, occurs. Precipitate. That means hydration product will begin to form and precipitate on the surface of cement grain. Okay. So the concentration of ions will be reduced. For the hydration to continue, the water will continue to dissolve more cement, release more ions into the water solution. So that is the third verb, diffuse, occurs. So water will diffuse through this hydration product, get into the cement, and release more ions. So these more ions will diffuse through the hydration product and get into the solution again. And then we have more precipitation. We have more hydration product. Okay, so that is diffuse, dissolve, and precipitate. Right, this is 8 hours. Okay, we can see more hydration product precipitate on this cement grain, and also we have more hydration product generate in the water solution. So when that happens, the cement is no longer fluid. began to become solid and gaining strength. 9 hours, we have more and more hydration products. We can see the needle-like hydration product, including CSH, calcium hydroxide, ethylene guide, and the monosulfide aluminate. They interconnect to each other. We call that mass precipitation. So the induction period, which is also called stage 2, is ended by mass precipitation of CSH. And the early hydration layer covering the cement grain transforms during the acceleration period. So far we only talk about C3S, but remember in cement we not only have C3S, we also have C2S, C3A, and C4AF. So we have more different type of hydration product including CSH, calcium hydroxide, AFT, which is ethylene guide, the needle-like shape. In the next lecture, we're going to look at this hydration product in details. AFM is also crystal, which is plate-like. So this is more realistic hydration process in cement grain. Then let's look at the particle size, the surface area, or we call that the fineness of cement. So when we get clinker, we need to grind this clinker into fine powder. So that's the last step in processing Portland cement. There's a specific surface areas, which is the total surface areas of 1 gram or 1 kilogram of cement. We should also measure the particle size distribution, which is the percentage for different particle size. Blade fineness, which is also called BF, is a measurement of air permeability, which is we can translate that into the surface areas of cement particles. For normal concrete, requirement is around 350 square meter per kilogram of cement. For type 3, it is a high requirement. Sometimes we blend Portland cement with some other materials. We call that pozzolans. Then we call that blended cement. Blended cement is specified by another ESTM standard, ESTM C595. So that's different type of materials. For example, slag. So slag is a so-called pozzolanic materials. Pozzolans including flash is also called coal ash. It's a byproduct of coal burning process. Silica film is another waste materials which is a byproduct of silicon production. Metakaolin is a byproduct when we treat the clay. So this is example of natural pozzolans. Natural pozzolans will react with calcium hydroxide, which is one of the product of C3S. They will generate CSH again, and we call that pozzolanic reaction. Pozzolanic reaction will be slower compared to chemical reaction of cement. So it has slower strength gain. It is also very environmental friendly because we use industry waste or natural pozzolans, so they do not produce CO2 as during the production process of cement. All right. There's a different type of blended cement, such as type S. Okay, so slag is byproduct of steel production. Okay, or type 1S is called Portland blast furnace slag cement. They have different percentage requirement for the slag. Or type 1SM is called slag modified Portland cement with different percentage requirement. So you do not need to remember all these details, but you should understand the important stuff, which is the chemical reaction and so on. Okay, so here are more details requirement for different type of blended cement, type P, type 1P, or type 1PM. Okay. Right. So let's look at the major difference between blended cement and Portland cement. Okay. The major advantage is lower heat of hydration. Okay. If we want low heat options, we can use either type 4 cement, or we can mix type 1 cement with Portland's. Okay, because the chemical reaction is slower, it will generate much lower amount of heat. It will also increase amount of CSH. As a result, the strength will be increased, durability will be increased, and also we save the energy. That is because we replace cement with waste materials. And remember, when we produce cement, a lot of energy is used. Okay, so if we can replace cement with waste materials, we can save the energy. Okay, but because we use the waste materials to replace cement, we may pay attention to quality control. Okay, so and also the slow strength development may be an issue for certain type of application. All right, so let's look at these materials in more details. So most of them are industry byproduct or waste materials. So typically, the price is cheaper than cement, except silica fuel. Okay, it is environmental friendly, okay, because they do not involve C2S emission as the cement production process. Okay, and chemically, most of these materials are mainly siliceous. Sometimes also has some alumina. Okay, so glassy or partially crystalline. Okay, so glassy means this siliceous materials is reactive. If they have a lot of crystalline, the reactivity may be lower. Okay, so these materials we call that pozzolanic materials. Okay, so pozzolanic materials will react with calcium hydroxide, which, as you remember, is formed between water and C2S and C3S. Okay, and here is the chemical reaction. We call that pozzolanic reaction. So the reaction between water and C2S and C3S will generate CSH, which is strong and durable, and also calcium hydroxide CH. Calcium hydroxide is weaker compared to CSH. It is also soluble in water, which means when we put concrete in water, calcium hydroxide may be dissolved, which is not good. Okay. So when we put pozzolans such as silica film, flash, or slag, so these materials which have mostly silica oxide will react with calcium hydroxide plus water. So the reaction is very slow, take several weeks or even months or years. It will generate CSH again. Remember, CSH is strong and insoluble to water. So basically pozzolanic materials will transfer the weaker and soluble calcium hydroxide into stronger and insoluble CSH. So that makes concrete stronger and more durable. So pozzolanic reaction is very beneficial to concrete. All right, so that's some other specialty cement. Okay, will not be discussed in details in this class, including white cement, okay, which the cement has a color of white color. Okay. This cement has no C4AF. Okay, the color of ferric will give a gray color of cement. Without C4AF, the color of concrete will be white. Calcium aluminate cement, this is a totally different set of cement than Portland cement. The chemical reaction is different, but this concrete can only use in cold weather. The strength is very high, but under warm weather, such as here in Hawaii, the concrete will shrink and crack, so we cannot use here. We could also have expensive cement for the situation when the concrete can have shrinkage cracking. We may want to use expensive cement. Concrete with expensive cement will increase a little bit in volume. Okay. We could also have rapid set cement or high early strength cement. So this is different from type 3 cement, also called high early strength cement, but the strength development is much faster. We can have very high strength within a few hours. Okay. So this type of cement can be used in situations such as emergency repair or precast or pre-stressed concrete. Okay. So these are some of the examples for specialty cement. Okay. All right. Okay. So that's the end of second lecture. Any questions about hydration of cement? So in this class, we discussed a lot of chemical reactions, reaction between water and C3S, C2S, C3 and C4AF. Okay, so a lot of information for you to understand and remember. Okay, so if you have any questions, let me know. If not,